Okay, if you have a nucleus of uranium 23592 and you throw a neutron into it, then it will split up into two light nuclei. One of the cases barium and krypton, along with neutrons, and also energy will released. So nuclear fission mean whenever a slow moving neutron incident on uranium 235, then it split up into two light nuclei, barium and krypton. 2 to 3 per nucleus neutron are released as well as energy is released. So before splitting up, this nucleus is known as parent nucleus, and these two nuclei are known as daughter nuclei. Nuclear equation: a neutron incident on uranium 23592. So this is most stable nucleus. As soon as uranium 235 will capture a neutron, it will change into uranium 236, or you can write uranium 236 and 92, and it is least stable. Means now uranium 236 will split up into barium 14156 plus krypton 9236 plus unknown neutron and energy. If you are looking how many neutrons are released during this reaction, I mean you are interested in this number, whether 2 or 3 neutrons are released, then we have to compare the mass number or nucleon number on both sides, which is A. First of all, see how many nucleons are on left hand side and compare it the number of nucleon on right hand side. So 236 on left hand side, 141 plus 92 and plus x neutrons. Make them equal, and from here you will see that x is equal to 3. It means during this reaction, in this particular reaction in which a nucleus of uranium 235 is split up into barium and krypton, the released neutron are 3. In the same way, if you are looking for whether the electron or proton are released during this reaction, then what you have to do, you have to compare the proton number or atomic number on both sides, that is G. So compare it. Left hand side, what is the proton number? 92. Right hand side 56 plus 36. So answer will be 0. This shows that no electron or proton is released during this reaction. Okay, one thing you must remember: before the splitting up into two light nuclei, it has less binding energy per nucleon, but as soon as it will split up into barium and krypton, so its binding energy will increase, yani more binding energy per nucleon. So it means barium and krypton are more stable as compared to uranium 23592, and this all happened because of mass defect. Okay, it is a quick revision. For example, here you have neutron, and what will happen? It will hit the target nucleus and it will split up into what? It will split up into two fission product, krypton and barium, and 3 neutron. 1, 2 and 3 neutron are released. So here the binding energy of target nucleus is less, and the binding energy of the fission product is more. So fission product are more stable as compared to target nucleus. Okay, fusion is reverse of fission, and in this case what will happen when two light nuclei, for example I have isotopes of hydrogen, when they will fuse together, I mean they are moving with very high energy, high kinetic energy in opposite direction, for example like this and like this. So when they collide with each other at high temperature, and this is usually happened inside the core of a star, these two combine together and it will change into helium. So here we have deuterium and here we have tritium. They will combine and they will change into helium. During this reaction, neutron and energy is released. So this is the main process that is going on inside the sun and all other star, and it is the basic source of energy, solar energy, that is produced inside our sun and other stars. So here binding energy, I mean on left hand side, binding energy per nucleon is less, and as soon as they will change into helium, the binding energy per nucleon will increase, and this all because of mass defect. So here you can see that deuterium is a positively charged and tritium is also positive charge. So it means there is a electrostatic force of repulsion between them. So they must have high kinetic energy so that they can overcome the force of repulsion between the positive charges. So in order to obtain this energy, a high temperature is required, and this high temperature is possible only in the core of the sun, in general a star, but particular for our solar system it is going on inside the sun. So as soon as they have enough energy, then what will happen, this and this, they are going to fuse with each other. As soon as they will fuse, then what will happen, they will form this configuration, and from here as soon as one neutron is released, they form a stable configuration, that is helium. So in this case the binding energy per nucleon of the isotopes of the hydrogen is less, so less binding energy per nucleon, and here more or high binding energy per nucleon. So in this way helium will be more stable as compared to isotopes of hydrogen.